Hello, everyone. Welcome. Thank you for joining us. My name is Carolina, and I'm here with my colleagues, Julia, Marcus, and Will. Today, we will be presenting Firefly. Firefly is an open source observability framework for serverless functions that provides key insights into serverless function health through the use of metrics and traces. Let's take a look at what we'll be covering in today's presentation. First, I'll introduce foundational concepts so that we can understand the problem that Firefly solves. Then, Julia will talk about serverless observability, why it's important, along with its challenges. She will also be discussing existing solutions in this space. Next, Marcus will introduce Firefly, give us a tour of Firefly's architecture. And finally, Will talk about the challenges we encountered and future work for Firefly. With that in mind, let's get started. What are microservices? Microservices represent a distributed architectural approach in which a single application is composed of a number of loosely coupled, independently deployable, and scalable services. Each service has a clearly defined role, executes its own processes, and often communicates via an API. Because of the abstraction of deployment and management of physical infrastructure away from the end user, the ability to build a microservice architecture has become more attainable with the rise of cloud compute. Microservices are now commonplace and provide an alternative to monolithic architectures. Let's get into what serverless is. Serverless is a development approach that allows for applications to be created and deployed without worrying about the underlying infrastructure of the system. In this development approach, the control in provisioning, maintaining, and scaling the server is typically handed off to a third-party cloud provider for a fee. Developers only have to provide application code, which will be packaged and deployed by the third-party provider. A microservices architecture can be composed of services deployed on their own servers, as well as services which are serverless. Serverless microservices are often built with one or more serverless functions. Serverless functions are small pieces of code designed to be asynchronously triggered based on events. Now, let's get into what functions as a service is. Functions as a service, or FaaS for short, describes the cloud-based service that hosts and manages serverless functions. To deploy a serverless function to a FaaS provider, a developer writes code that fulfills a particular purpose in the application and defines an event that will trigger the function. Once the event is triggered, the service provider, called Cloud Listener in this diagram, starts a new instance of the function, work is performed, and the result is returned. As more events are triggered, the FaaS provider is responsible for automating the provisioning of computation resources and scaling instances in response to demand. This eliminates the need for frequent hands-on management. This is contrary to a system where a service is deployed on a server, which the developer has to manage. The server is kept continuously running, ready to respond to any incoming requests. If demand increases more than the server can handle, requests are ultimately refused and scaling will need to happen manually. In this diagram, you can see that there is a request response that happens when the function is invoked, along with an increase in compute resources. Compute resources stay stagnant when the function sits idle and spins down, and it'll increase again when the function is invoked and spins up again. But what does this mean? FaaS providers only allocate compute resources when a function is invoked. So when demand decreases and the function sits idle, resources are deallocated and functions do not use compute. As a result, serverless functions are not required to reserve and hold computational resources in advance, as is the case with traditional architectures. This auto-scale auto-provision, and compute per use model allows developers to save time because they are free from implementing, troubleshooting, and maintaining servers. Unfortunately, the inability to access or modify the cloud provider's environment and infrastructure makes it challenging for a developer to collect data about serverless functions compared to applications running on traditional servers. A different set of strategies is required, which we will be discussing later. This diagram represents the three most popular serverless function cloud providers. To wrap up this section, let's get into what is observability. The following quote is an observability definition that we found most helpful to us from Honeycomb's O'Reilly book, Observability Engineering. Observability is the measure of how well you can understand and explain any state your application can get into, no matter how novel or bizarre. A software system, when reduced to its most basic purpose, should take an input, perform some form of computation, and produce an output. Observability is concerned with the data generated during this process. This data is called telemetry data. Telemetry data is the data generated by the system that pertains to its behavior. Using this data, we are able to gain a better understanding of the internal state of the system from the outside. The inner workings of the system do not have to be known to ask and answer questions about it. So, the more observable a system is, tracking down potential issues and onboarding new engineers becomes easier. In order to generate telemetry data, a system must be instrumented. Instrumentation is the process of adding code to your system in order for it to generate and emit telemetry data. Observability focuses on three main telemetry data types: metrics, traces, and logs, the three pillars of observability. Metrics are numeric, quantifiable measurements that reflect the health of infrastructure aggregated over a defined period of time. Here's an example of Firefly's dashboard showcasing key metrics for serverless functions, which include invocations, errors, and duration. These metrics are vital performance indicators for a system, enabling engineers to identify patterns and anomalies. While they are able to quickly indicate the presence of an issue, they are not sufficient for pinpointing the exact source of the problem within a program. A log is a time-stamped message, which can either be structured or unstructured. It is a record of a specific pre-configured event that happened at a particular time during the request lifecycle. Here's an example of a dashboard showcasing logs. Logs provide granular insights that a metric cannot. However, their volume of generation causes them to be difficult to manage. Logs aren't useful for tracking a request through its lifecycle, but they do come in handy once a greater amount of granularity is required. Moving on to what traces are, I'll first introduce what distributed tracing is in order to fully understand traces. Distributed tracing is the process of tracking a single request as it makes its way through the different parts of an application. A trace is a term used to describe the visual representation of this tracked request. Here's a snapshot of Firefly's dashboard showcasing traces. Traces significantly reduce the complexity that arises from the nature of distributed systems, where reproducing failures locally can be overly complex. Tracing makes debugging considerably easier as we are able to break down each step in a given request. Let's walk through this to get a clear picture. In this diagram, we can see the components that make up the system, but we aren't able to see how a request would travel through it, or which point in the request lifecycle causes the request to fail. This is where distributed tracing comes in. This diagram displays a trace in its entirety. Each component is referred to as a span. A span represents a unit of work and the time taken to complete that work. The first span in a trace is the root span. It generally represents a request from start to finish. In this case, the root span is the web application. The spans underneath are child span. Each child span represents a unit of work within that request journey. Let's go through the request flow for this particular trace. Web application calls service A calls service B and waits for a response. And then service A calls service C and D. In order for spans to become a distributed trace, certain metadata representing a shared state called context needs to be passed at each part of the request execution. This can be used to correlate the spans into a single trace. This mechanism is known as context propagation. Requests carry this information throughout their lifecycle, allowing each generated span to have access to the shared context. Context propagation is what makes distributed tracing possible across a distributed system. Now, I'm going to hand it off to Julia, who will expand on serverless observability, why it's important, and how it's challenging. Take it away, Julia.
Thanks, Carolina. So, why is serverless observability important? Well, to reiterate again, to increase observability, the application must be instrumented to emit telemetry data. That data is then used to gain insight about the state of the application and the requests passing through it. For an entire system to be observable, each individual part of that system must be observable. For a system spanning multiple services interacting with each other, only instrumenting one service out of many is insufficient. Each part of that system must be instrumented, and the same applies to any serverless functions in that system. Let's go over an example. Here we have a web application which can make requests to two different microservices, service A or service B. On top, service A is composed of a series of serverless functions. Below that, service B is a more traditionally hosted microservice running on a VPS. If reports start arriving of a slowdown in service A, troubleshooting would involve more manual work, checking each function individually to verify which function might be underperforming. If the functions were to be instrumented and observable, we can see much more quickly which specific function is a source of the issue based on emitted telemetry data. This allows us to hone in our efforts on the problem faster and optimize the function as required. What then is challenging about serverless observability? Well, there are two main problems, the first of which being the instrumentation approach. In traditionally hosted applications, many observability strategies install an agent within the application's environment. We can remote into each server and start a process which will send telemetry data. This agent is then responsible for collecting that data and temporarily storing it until it can be emitted to a telemetry system. For services composed of serverless functions, the agent-based approach poses a problem. Because the FaaS provider takes care of managing underlying infrastructure and function deployment, we can't easily access or remote into that function's internal environment. Separate processes can only be deployed directly by the FaaS provider. Regular user-installed agents are not suitable for instrumenting serverless functions. Furthermore, serverless functions are ephemeral and stateless. There is no built-in persistent storage or state. Any data saved locally is lost when the function environment spins down. Normally, as long as the generated telemetry data is emitted to storage external to the function before the instance is destroyed, this isn't a problem. However, if the FaaS provider destroys the function instance before the telemetry data is emitted, then the data becomes lost due to the lack of persistent memory. After the instrumentation approach, the second of the challenges in serverless observability is context propagation. Context, as Carolina already mentioned, context propagation is a mechanism by which distributed tracing occurs. Information about the context for a given initial request is passed along to downstream services as the request continues through the system. This allows telemetry data generated by a given request to later be linked together in an observability solution, ultimately showing how each service is involved in the request's lifecycle. For microservices that interact in a well-defined request-response cycle, the relationship between those two services is clear and defined. Service B sends an HTTP request with all necessary information, including the context. And Service C sends a response when the request is processed and complete. There's a well-established standard for this communication. For serverless functions, which are invoked asynchronously via events, this relationship is more hazy. A request from a client results in an event being sent to enter an event queue. Functions subscribed to the queue are invoked as a result and process the events one by one. Any necessary data that might have been sent with the initial request may not be attached to the event and accessible by downstream functions. The mechanism for ensuring this is vendor-specific and dependent on the FaaS provider. In order for context propagation between two services to be successful, both sides must agree upon a convention. And for a system which may span multiple hosting ecosystems, this convention must be vendor agnostic. In summary, serverless observability is important for overall system observability and optimization, but it's challenging to do due to available instrumentation methods and context propagation. Fortunately, there are available solutions that can be explored. Developers looking to increase observability of their serverless functions have a few options. Vendor-specific solutions from the FaaS provider, software as a service solutions, or do it yourself. Different FaaS providers often have their own solutions with their own set of conventions, dashboards, and APIs to access the data. Let's take a look at AWS, for example. AWS provides CloudWatch as its native observability solution. The advantage of using CloudWatch is that there is no instrumentation work required. Metrics and logs are collected by default, and tracing is enabled at the flip of a switch. Along with that comes a managed data pipeline that you don't have to set up or scale. However, despite being easy to set up, there are a few disadvantages. Billing can be unpredictable and confusing due to a variety of different features such as queries, dashboards, alerts, which are all charged separately. This results in the amount you ultimately owe to quickly become difficult to predict and track. CloudWatch also offers no global overview of your telemetry data, with each telemetry type being separated into its own dashboard. A key part in being able to increase observability is to be able to make associations between different types of telemetry data. To see the state of the service via metrics, then flip to traces to see its effects on requests. Using CloudWatch means you have to switch between dashboards to do this, adding unnecessary friction. Finally, using CloudWatch also means your observability data is stuck within AWS. This is problematic if a system also contains non-AWS hosted services, as observability data across the whole system cannot be cohesively accessed from a single source. To get a picture of your overall system health, having one solution that is able to incorporate your entire architecture is of high importance. Software as a service or SaaS solutions are the next logical choice to explore. There are many vendors available, as you can see from the logos on the right. They range from serverless only to full stack observability solutions. As with FaaS provider solutions, SaaS solutions have easy automated setup and data pipelines which are managed by the service. SaaS solutions also often provide extensive battle-tested feature sets, which may go well beyond serverless functions. All of this is contained in a generally effective and appealing central UI. However, similarly to FaaS solutions, SaaS solutions also come with high unpredictable costs, which may take up 30 to 50% of your total infrastructure costs. And problems of data control and ownership still remain, as observability data is all sent and stored with a third party, creating vendor lock-in. If you needed to switch observability vendors down the road, it's likely to be a challenging and tedious process. A do-it-yourself solution may alleviate many of the issues seen with a SaaS provider or a FaaS-specific option. High and unpredictable costs in using this system and vendor lock-in issues can be mitigated by the use of free-to-use open source tools. But while DIY solutions provide users with control, freedom, and flexibility, the work required to set up a solution is great. Considerable prior research needs to be done to understand serverless observability, how all the components of a telemetry system need to interact, and the options available for use at each step. Documentation may be confusing or non-existent, adding additional frustration. And once research is complete and components are chosen, putting it together and tuning it to suit your needs may be additional weeks or months of work. So then, what alternatives do we have? I'd like to hand it off to Marcus to talk about Firefly.
Thanks, Julia. So, as Julia has mentioned, there are quite a few options when it comes to observing serverless functions. So where exactly does Firefly fit into this picture? Well, firstly, it's an open source observability framework for serverless functions. But what exactly does that mean? In short, it means that it can provide key insights into serverless function health through the use of metrics and traces. It does this by automating function instrumentation as well as deploying a telemetry pipeline. Once you've deployed Firefly, you'll then be able to see all your data in a number of easy-to-use dashboards. So with that in mind, let's move on to what the goals were for the project. There were two main goals for the project, and the first was to make sure it was easy to deploy and use. We wanted users to be able to get up and running quickly and have no issues with finding the key information required to track down problems. Secondly, we wanted Firefly to be vendor agnostic. So for example, if a user wanted to stream their data to a different observability system, they could. So what specifically does Firefly focus on? Well, the first is it was built for serverless functions. Firefly isn't intended to be a complete observability tool covering your entire stack. The second focus was narrowing the scope to AWS Lambda functions. As you probably know, AWS has the largest share of the cloud market, so there's a good amount of developers who are already familiar with the platform. And finally, the last focus of the project was concentrating on metrics and traces, not logs. So if you wanted to start using Firefly, it's just a two-step process. The first is deploying the telemetry pipeline, which is done via Docker. And the second step is running through Firefly's command line interface. This ensures your functions are instrumented so they can start generating and emitting telemetry data. So once these steps are complete, you'll then be able to view the data in Firefly's UI. We end up using Grafana as our monitoring and visualization tool, and then build a number of dashboards for serverless functions on top. So when you load the UI, you'll be greeted with the main dashboard, which provides a general overview of all your serverless functions. As you can see, we have graphs that display each of your function's key metrics, as well as a table below highlighting the same data in statistic form. When you want to dive deeper into a specific function, you can simply click it from the function list. This brings up the function dashboard, which includes additional key metrics and trace data. So along the top, you can see stats for invocations, cold starts, errors, duration, and memory utilization, and then relevant graphs for those metrics and others as you scroll down. As you reach the bottom, you'll also be able to see all the individual traces for that function. This gives you a quick overview of the trace duration, but also allows you to see if there is an exception on the right-hand side of the table. If we then click on an individual trace, you'll be taken to the trace view. Within the trace view, you get a much finer overview of the specific trace, as you can see exactly which services are calling which and the associated latency. It's a great way to see which services are underperforming in a quick glance. Now, if we then click on an individual span, you get even more detail. So, as you can see, the data is a lot more granular. You're able to see specific attributes of that request, as well as showing any relevant event information. So now that we've seen how Firefly can be deployed and utilized, I'll run through the different components that make up its architecture. Telemetry systems, such as Firefly, are made up of three main phases: emitting, shipping, and presentation. The first phase is the emitting phase, and its purpose is to collect and emit telemetry data. And it does this through the instrumentation of application code. The second phase is the shipping phase. Its job is to receive the data sent from the emitting phase, process it, and then store it within a database. The third and final phase is the presentation phase, and its sole purpose is to retrieve the data stored in the shipping phase and then display it to the user. So let's run through each phase in a bit more detail. Starting with the emit phase, you can see the Lambda function in the top left of this diagram. Now we need to be able to get telemetry data out of the function. This is done in two parts. The first part is trace emission. And the second part is metric emission. So let's start with trace emission first. We handle trace emission through a two-step process. The first step is instrumenting the serverless function so spans can be created and emitted. The second step of the process is making sure spans are assigned the correct context when the function is sent an event from an upstream service, otherwise known as context propagation. Now, for the first step to be accomplished, we need a way to instrument the function. And for that, we use OpenTelemetry. OpenTelemetry is an open source toolchain that can be used to generate, collect, and export telemetry data. It was created due to all the observability providers having a different way of instrumenting application code, which meant switching providers was difficult. So ultimately it was decided that an industry standard was required, which thankfully OpenTelemetry has now become. So because one of our main goals was for Firefly to be vendor agnostic, it made sense to incorporate OpenTelemetry from the outset. Now, the key component we use from OpenTelemetry is the collector. It allows us to receive, process, and export telemetry data in numerous different formats, which is perfect for our use case, as you'll soon see. The diagram here just shows a high-level overview of how an OpenTelemetry collector is composed. So it receives telemetry data, processes it, and exports it to a given endpoint. We actually use the collector in two locations within Firefly's architecture. The first of which you can see on the left of this diagram attached to the Lambda function, labeled as AWS distro for OpenTelemetry. The distro has AWS's own version of the collector that includes additional code for auto instrumentation. And this is the key point, as it allows the Lambda function to generate and emit spans. Now, it's worth mentioning how the AWS distro is added to the Lambda function, as it's also important for the second step in the trace emission process. In AWS terminology, it's referred to as a Lambda layer. And it's just a way to package code that you can use within your Lambda functions. They can contain a number of different things, such as libraries, custom runtimes, data, or even configuration files. So now we know what a Lambda layer is. This leads us on to the second step of the process. Let's just quickly remind ourselves exactly what that is. It's ensuring spans are assigned the correct context when they are sent an event from an upstream service. So we're then able to join these spans together in the presentation phase to form a distributed trace. Unfortunately, this wasn't handled by the AWS distro of OpenTelemetry. So we decided to build our own layer, which you can see just above the AWS distro. The Firefly layer is what enables us to handle context propagation. So when an event hits the function, the correct context from the upstream service is extracted by this layer and then inserted into the event going to a downstream service. Don't worry if this is a little confusing now, as well as to go and discuss this in greater detail in the challenges section. So you can view the layers as a formal middle layer. They do all the relevant work to the incoming event and allow Firefly to properly handle trace emission. Let's now have a look at metric emission. Metric emission is handled by three services: Amazon CloudWatch, the CloudWatch metric stream, and the Kinesis data firehose. So let's zoom into that process. AWS Lambdas automatically report metrics to Amazon CloudWatch. This is handy for us as it allows us to extract that metric data from CloudWatch. Now, the way in which we do this is through the CloudWatch metric stream. When CloudWatch receives a metric update, the metric stream kicks into action and emits the relevant data to a given location. That location in Firefly's use case is the Kinesis data firehose. The firehose receives stream data, transforms it, and then sends it to a given endpoint. Not too dissimilar from what the OpenTelemetry collector does. Using the firehose, we can then direct the telemetry data to the shipping phase. And that's it for metric emission. So let's move on to the shipping phase. Now, as I mentioned earlier, we use two OpenTelemetry collectors within our architecture, the second of which you can now see at the entrance to the shipping phase. It's Firefly's own build of the OpenTelemetry collector, which acts as a gateway to the shipping phase. The reason for using a second collector is because we have two different emit sources. For traces, the AWS distro for OpenTelemetry. And for metrics, the AWS firehose. This means the data is in different formats when it arrives at the gateway collector. Not only that, but metrics also have to be sent to PromScale, the connector for our database, in a different format again. So if we now visualize our second collector, you can see we receive trace data in OpenTelemetry format and metric data in JSON format. This data is then processed and exported in OpenTelemetry format for traces and Prometheus format for metrics. This enables PromScale to receive the telemetry data in the formats it works with and then structure it for entry into the database. Once the data is stored, it's then ready to be queried by the presentation phase. The presentation phase has one aim, and that's to retrieve and display telemetry data. Our dashboards send queries to PromScale to retrieve the necessary telemetry data and then present it to the user. So, pulling this all together, we have the emit stage on the left, which enables trace and metric emission from the Lambda function. In the middle, we have the shipping phase, which receives the data from the emit phase, processes it, and then stores it within a time series database. And on the right, we have the presentation phase, which, as just discussed, then retrieves the telemetry data from the database and presents it to the user. So hopefully you've now got a bit of a better grasp on Firefly's architecture. With that said, I'll now hand over to Will, who will discuss some of the technical challenges we faced.
Thanks, Marcus. I'll be going over some of the technical challenges we faced while developing Firefly, namely distributed tracing and context propagation. Distributed tracing is the act of tracking a request across a system. Context propagation is the means by which this is achieved. As a request goes from service to service, a context object is passed along with it. This passing of context can be performed using dedicated HTTP headers embedded in the request. Those headers would contain information that includes a trace ID and a parent spans ID. Then services downstream would be able to parse the information and assign the correct trace and hierarchy as it generates spans. There are several different protocols for context propagation, and each protocol has its own convention for headers and formatting for associated values. Services communicating with each other have to ensure that they share the same protocol in order for propagation to be successful. So now I'll go through how this should work in Firefly. The AWS distro for OpenTelemetry, or Layer, acts as a middleware for the Lambda. It handles tracing and context propagation. Using OpenTelemetry API components, the layer should parse context information from incoming requests. It should create spans with the appropriate context, and then it should inject context into outgoing requests. But this is not what happens. What actually happens is the AWS Lambdas and the Layer default to using AWS-specific headers to propagate context. These headers are not supported by OpenTelemetry. When using the Layer, our Lambdas can only parse OpenTelemetry-supported context formats, and they can only inject AWS-formatted context to outgoing requests. So when the Layer sends these AWS headers downstream, and the downstream service is instrumented by OpenTelemetry, it can't parse the headers, and we lose context. But all is not lost. Instead of using the default context propagation method, allows us to switch to other methods of context propagation. And we switched to W3C trace context propagation method, which is supported by OpenTelemetry. So the W3C propagation method uses a header called trace parent. That header contains the trace ID and parent spans ID that allow us to pass context. By switching propagation methods, OpenTelemetry's context propagation, By switching propagation methods, OpenTelemetry's context propagation API on the layer is able to look for the presence of the trace parent header. It can then parse context appropriately and inject a new trace parent header for outgoing requests. So we've solved this problem, but we're not out of the woods yet. While OpenTelemetry's context propagation API has no problem finding the trace parent header when a request follows the standard HTTP format, such as functions invoked through an API gateway or via a URL, this is not the typical way that serverless functions are invoked. We tend to think of serverless functions in terms of events and not requests. SQS and SNS messages are the most popular methods of invoking Lambdas. These more popular methods still have some issues we need to solve. In addition, functions invoked via AWS SDK also need some work. In the case of SQS SNS events, the trace parent header is injected in a non-standard location. So it has the header, but the layer can't locate that header and will assume that it's missing. It will use a new context when it creates a span. This new context will have a new trace ID, and we lose context. We solve this by wrapping the function and intercepting incoming events. When the trace parent header is parsed, the span is created by our instrumentation and reassigned to the correct context. And then Firefly's Lambda layer invokes the function. So we've solved our context propagation issue with our Lambdas invoked via SQS and SNS events. Now let's move on to AWS SDK invoked functions. So the problem with functions invoked via AWS SDK is slightly different. the OpenTelemetry propagators are able to inject the trace parent header into the request, but the invoked function doesn't receive the full request, only a designated payload. And that payload doesn't contain the trace parent header, which means we lose context. So we solved this by creating a wrapper function for AWS SDK Lambda invoked functions. The wrapper injects the trace parent header into the payload, which allows context to be parsed properly. So that about wraps up our context propagation issues, and I'll just mention a few things that we could improve in the future in Firefly. So Firefly currently works well for AWS Lambda functions using Node.js, but we'd like to extend our language support to Python, Java, and Go. We'd like to provide observability solutions for serverless function providers in addition to AWS. So providers like Microsoft, Google Cloud, and Cloudflare. And we'd like to implement metric emission via Firefly's Lambda Layer once OpenTelemetry's Lambda Layer support matures. Okay, so now we'll move on to the Q&A. Feel free to ask us questions, and we'll do our best to answer them.
Looks like we've got one question just in the Zoom chat, and that's what was the hardest part of the project?
You want to take that one, Marcus?
Yeah, there was a number of different parts, to be honest with you, that proved quite challenging as they popped up. The context propagation was definitely one of them. But to be honest with you, probably one of the things that we had to deal with initially was just the sheer amount of different sort of open source solutions that could potentially help us with our problems, and having to actually narrow that down to something that we could use in a manageable architecture. You know, the amount of documentation that you have to go through, and it being really quite sparse and unsupported in many ways. We often were coming across GitHub issues for the projects that we're using, such as OpenTelemetry, that had been opened like last month, for example, and we were coming across these problems quite regularly. So that was also another part of it. But yeah, among many others. So thanks for the question. That was a good one.
Okay, so we have another question. What's been each of your favorite parts about building Firefly? And I guess my answer maybe is a cop-out. I'm not sure, but I just really enjoyed like learning everything about context propagation and how to open telemetry and just how to connect all the pieces together. It was very enjoyable for me.
I can add on to that. I think one of my favorite parts was like letting go and trying things out, getting your hands dirty. There was a point where we were trying to extract metric data, and like Marcus went in one route, and then Julia, Will and I went another route, and just like trying things out, reading through documentation, trial and error. I think that was my favorite part. Yeah. I don't know if anybody else wants to share.
I did not enjoy reading the documentation, but
yeah, I'm weird.
Yeah, I think my favorite part was just that day that we first got everything working in the system, and we started managing to get telemetry data coming through and being able to see it. That was, yeah, very gratifying to say the least.
Yeah, I would agree with all of the above. I think overall, kind of like stumbling upon this problem domain and then realizing that there is a project to be had here just based on all of our experiences on trying to put together all of the open source tools and setting up the instrumentation and whatnot. Yeah, I think that probably was one of my favorite feelings, because I was like, oh, finally we're doing what actual engineers have problems with. So that was very cool.
oh, okay. It looks like we have another question. And then chat talking about how we use Amazon CloudWatch for the metric stream. So with accessing CloudWatch via Firefly, avoid the costs of things like the FaaS solutions with their unpredictable costs. Julia, do you want to take this?
Yeah, yeah, that's a really good point, and that's very astute. Keen eye for detail. So yeah, ultimately, I think as Will has mentioned, one of our future works is to actually use our Firefly layer for the metrics instrumentation, so we don't have to go through CloudWatch. But until we got to that point, our goal was to get metrics in any way possible, and so we did decide trying to pull it from CloudWatch was the best option. There are still some nominal costs involved, but because we're not using all of the full feature sets of CloudWatch, it's not as high as still using like CloudWatch built-in. And yeah, when we justify that also with the fact that we do provide a much more comprehensive UI, I believe, compared to what's like natively available in CloudWatch to use. So some costs, but not all the costs of using the full out CloudWatch solution.
Yeah. Okay, so another question. Great logo, thank you. Did you happen to get a chance to try some alternatives to prom scale, or was it perfectly suited for your use case right out of the box? We actually, I think we talked about using other solutions, but we did a lot of research, but prom scale kind of fit what we were trying to do. I don't know if you want to elaborate any more on that, Marcus, but
yeah, we looked at Elasticsearch and TimeStream, and the likes of Victoria Metrics as well. One of the things that we found was they were very good for their particular niche, but the problem was they were just serving either metrics or traces. And then once we came across PromScale, it just worked perfectly for our use case. As the question says, it did just seem to fit it perfectly. So we did a comparison, and then once we got PromScale working, it seemed to be the best fit. So being able to store both metrics and traces. So yeah.
yeah. And next question, did you create documentation for Firefly alongside developing the program, or is it easier to put together after the project is fully functional? I think our project was, we were changing so much as we went,
Yeah.
or that we didn't really make documentation alongside it. I would imagine that like a bigger project, or depending on the project, you might want to create documentation as you build pieces to it. But it was just we kept changing, the pieces and trying to fit in the best pieces to our overall architecture. So we didn't create documentation alongside it.
Yeah, there was definitely a lot of just-in-time learning and just putting in the code and seeing if it works. Configuration, I think we went through a lot of configuration. So for us, I think it would make more sense to do it after, just because of all the changes of implementation that we went through. So good question though.
So I guess that's it. I want to thank everyone for attending